So welcome to the second lecture, and today I will talk a little bit, continue the discussions about basics of machine learning, and especially we will talk about decision trees. So machine learning is of course important part of data mining, and I've talked about some of those things before. But basically, if you think about why we are trying to do machine learning, what do we want to achieve with machine learning that's not possible to achieve otherwise, there are basically three main reasons for using machine learning. One is knowledge discovery, which is basically when we are trying to learn new things and improve decisions in a way that we don't know something interesting. So for example, when we try to go from medical records to medical knowledge, we have a list of patients and what have been done to them, how it worked. We want to extract new insight into what's possible, what works, and so on. The other direction or other aspect of it is software engineering, which is basically if we have tasks which are too difficult to program, we can try to use machine learning in order to learn it from examples. So if we talk about autonomous driving or speech recognition, those are tasks which we are basically unable to write programs for, even though we kind of know how it should work. It's just too complicated. So machine learning helps. And finally, when we want to have programs which are self-customizing, so basically program which is not always the same. For example, when it adapts to a particular user, particular domain. So if we want to have a newsreader that learns each individual user's interests, those are things where also machine learning is helpful. So if we think about what do we want to really do, the fundamentals for learning are always the same. So it's basically always we look at a particular set of possibilities. So we say we have some kind of a hypothesis class. We adjust our predictions based on the available examples. So from this hypothesis class, we pick the ones that look the most useful or that look like are most suitable for the examples that we are working with. So this is called model selection. And then we potentially do it again if we are getting more examples. If we do it in some kind of online continuous fashion, we all the time redo this estimation and selection. If we only have one batch of examples, we do it once based on all of our examples, and we say, okay, here is the best possible hypothesis. And those kinds of principles, they are universal. You can think of this type of learning happening in society. If you think of societal scientific community or government, you can think of it. Individuals learn as well. Like humans, animals, everybody tries to learn based on experience. And then we try to kind of give the same abilities to machines. And if we talk about specifically machine learning, there are three main ways of doing machine learning. So one is called supervised learning, and there we have explicit goal information. So we know exactly what we want to achieve. So the goal here is to emulate some kind of oracle based on examples of operation of this oracle. The other approach is semi-supervised learning, where we have some number of labeled examples like this, but we also have a number of examples without labels. And those examples are useful for learning the overall data distribution, even if we don't know what should be the decisions for them. And here we can distinguish different approaches. So we can talk about active learning, where we are allowed to ask queries about some number of examples. So we want to find the most informative ones to query. We can talk about reinforcement learning, where we have delayed or partial feedback, and we look for ways to utilize this. And then we can also talk about unsupervised learning, where there are no labels, no goal indication from the oracle. We just want to identify structure which is inherent in the data. And today I will be talking about supervised learning. So we only consider cases where we actually have correct labels for the data that we are interested in doing. Later in the course, we will talk about some of the other ones as well. So,
Slavomir?
Yes?
Can you just go back to the previous slide, please? Yeah, just a short question about semi-supervised learning. What's meant with show overall data distribution? Is it to categorize the data into main categories, or?
Well, so the point is, so one example of semi-supervised learning would be for either image classification or document classification, where you have, let's say, image classification. So we have some number of training images. Let's say you want to distinguish cats from dogs. You have some number of labeled images, but then you also have access to a lot of images. Basically, getting examples of images is not difficult. It's difficult to label them, or it's expensive to label them. If you need 10,000 labeled examples, that's a challenge. If you just want 10,000 examples, that's not a challenge. You can get them basically for free. So here the question is, how can you take advantage of all of those unlabeled examples? And they will basically tell you how images look like. They will not tell you which of those images are dogs, which are cats, but they will still be useful. So there are techniques of taking advantage of this even without the labels.
Thank you.
So the core of supervised machine learning is about model selection. So what you basically want to do is you want to have some kind of a model which distinguishes between, let's say, two different classes of points. You can represent your points in multi-dimensional space. If you want to visualize it, of course, 2 dimensions is nice because you can show it. Anything beyond 2 dimensions becomes harder. So there will be plenty of images looking at 2-dimensional data, even though this is not really that useful, because if the data is 2-dimensional, doing machine learning is really not challenging. But the core of machine learning is basically figuring out what should be the separation between, let's say, red and blue points, just as in here. And you can have a lot of different ways of doing the separation. Here you have different order of polynomials, from linear to 8th order polynomial. And basically, the whole interesting thing about machine learning is that it's hard to say which of those is better. Right? If you look at those particular images, the 8th order polynomial looks nice because it allows you to actually separate all the red points from all the blue points. But if you think about it, it's unlikely to really be correct. It looks like the linear one might be more correct, or maybe 4th order polynomial is closer to the kind of ultimate ground truth. So it's always a little bit of a question, what exactly do we want to achieve? There is not necessarily a very clear, well-defined way of saying how good our solution is. And I will talk more about how we can actually do this. The other important part about supervised machine learning is about data representation. Right? So let's assume that we have an image like this, and the label here is yes. And we have another example, image like this. The label is also yes. And we have this image where the label is no. Any idea what this could mean? Any guesses? What could we be trying to learn?
If this image is part of this class or not?
Yes, but what class we are trying to learn? Those images look like anything? So those are actually digits.
Yeah, the third one is a 3?
Yes, the third one is 3. The first 2 images are digit 2. So we are trying to learn if the image actually represents the digit 2 or not. Right? So just a binary classification. The first 2 images are examples of digit 2. The third one is not. And it doesn't really look like digit 2, but if you look carefully enough, you can find it. This is from the data set from US Post. So this is how people write on the letters. They were interested in figuring out, can we actually automatize understanding those digits? So the important thing here is, if we have those kinds of images, there are a lot of different ways in which they could be represented. Right? So here is just a pictorial representation of this. And it's important to understand that the data that is presented to a machine learning algorithm, this is just one way of modeling some kind of reality. So those are images that were taken from actual letters, scanned, discretized, and so on, turned into black and white images. You could have a lot of different ways of representing this. So for example, instead of an image like this, you could have a long string of digits just representing whether a particular pixel is white or black. And if you look at this, it contains exactly the same amount of information, but even for us humans, the red string would be a lot harder to make sense of. Right? If you would see many strings like this, you wouldn't be able to figure out easily which one corresponds to digit 2 and which one doesn't. And it's the same thing with computers. Depending on how you represent your data, the problem will be very easy or very difficult generally. So this is why topics like feature engineering and understanding of the domain is so important if you really want to have practically successful machine learning. If you find good features, if you have good representation of the data, the machine learning will be much more successful. And the only way you can really do this in general is if you understand what is important in the domain. So here, of course, what is important is the spatial relations between pixels, which is why if you just kind of unroll all of this into one long string of bits, it becomes much harder to find the patterns which are actually interesting. So this is the core idea behind supervised learning. The supervised learning is about finding a mapping, let's call it H for hypothesis, that goes from space of examples, so let's call it X, into space of labels. So basically, you want to have a function which for every example will assign a label. So is it digit 2 or not? Is it dog or cat, and so on. And you have to have a restricted subset of all the mappings. You could imagine a hypothesis space in which you consider all the possible mappings. But that doesn't work. We will go a little bit deeper into this later today. So you need to pick a particular type of hypothesis that you are interested in, and then you need this hypothesis to actually use representation of examples, not examples themselves. So most commonly what you will do is you will represent your examples as points in a feature space. So if your example is an image, you would have a number of pixels. So you could imagine that this is a space. If your examples are movies, you would represent them with certain features like the genre, the actors who play in it, the director, title, whatever else. If your examples are different kinds of vehicles, you would represent them based on some data collected on those vehicles and so on. But either way, you have some representation of the examples. You can think of it as multidimensional feature space. So then each example belongs to a feature space of, let's say, m dimensions. And that means that whatever functions are kind of well aligned, or whichever functions look nice in this particular space, are more likely to be chosen as a hypothesis. So that means that there are two types of bias that you introduce into your machine learning algorithms. One is what types of hypotheses you allow and which ones you don't, or which you prefer and which ones you don't. And then the other type of bias is how does the representation that you use for your examples align with this hypothesis space. So this is something, again, that we will explore a little bit more. Next important concept related to supervised learning is the evaluation. So basically, how do we know if what we have learned is actually good? So the ultimate goal is what is called good generalization. So basically, what we are interested in is not how well the hypothesis we are looking for or we are finding agrees with our training data, but how well does this hypothesis agree with all the examples in the whole possible space? So the tricky thing is, of course, how to estimate it. By definition, we don't really know anything about unseen examples. So how can we know if our hypothesis works well on those or not? We can measure the agreement between our hypothesis and the kind of underlying function which we are trying to learn based on the training set, because for the training samples, we have the description of the example, we have the label, we can check what is the answer that our hypothesis gives, what is the original label, and we can see, is this the same answer or not? If there is some disagreement, we know that our hypothesis makes a mistake. But how can we know anything about unseen examples? And here is the most important assumption that comes into supervised machine learning, is IID assumption, so independent and identically distributed. So what we basically start the whole concept from is that we assume that every example label pair that we have in our training set, so we have example xi and corresponding label yi, this is drawn from some probability distribution. So there is a population of possible examples with some kind of probability describing which examples are more likely or less likely to be drawn. And we assume that our training set comes from this particular distribution. And then we assume that whatever our hypothesis or our model will be tested on will be drawn from exactly the same distribution independently. So every single example is drawn independently from each other according to the same distribution. This is a very strong assumption, and it's not always fulfilled completely in practical cases, but this is what kind of underlies all of the theoretical analysis of machine learning. That basically we assume that our training set is representative for the type of data that the hypothesis will then be tested on. So we can measure the training loss empirically. We actually can figure out how much different our hypothesis is on the training examples. And then we can probabilistically measure what is the expected error that our hypothesis will make according to this particular probability distribution of samples. And what we are interested in is minimizing this expected loss over new examples that we haven't seen yet. That's kind of the core of this. And obviously, it's not very surprising that as the number of training examples increases, our solution that we can get is better. So here is just a simple example. You have some number of points, you want to fit a line to it. The more points you have, the closer will be to the correct underlying, the real line that those examples come from. So you can measure what's the mean squared error between your line and all the examples, and you can see that it reaches a certain level, kind of drops down at the beginning, and then it tapers off at a particular level. So it improves for some number of examples, but then at some point you reach a stage where you get more training examples, but the function doesn't improve anymore. And the question is, of course, why? So is there always such a limit? And how do we figure out if we have already reached that limit or not? So if you think about what is the error that machine learning performs, there are basically two kinds of error. One is structural error, also called bias, and the other one is approximation error, also called variance. And it comes from two simple observations. The structural error is the error which is introduced by the limited function class. So by the fact that our hypothesis space is not complete. There is only a particular type of hypothesis that we are interested in. So for example, in the previous case, it was we are only looking for straight lines. So if the data is not really a straight line, we will always have certain amount of error that we cannot remove. And then the other part of it is the approximation error, which basically means how close can we get to the optimal performance based on our limited training data. So if you only have few data points, you don't know which of the possible lines is actually the best. Assuming there is some noise in the data, of course. If there would be no noise, 2 points would be enough. But with noise in the data, you need certain number of examples before you can reliably say what are the correct parameters for the line you are looking for. So if you look at the equations for this, I will not go into details here. You can look at it later if you want. It's basically you can separate those two parts based on the estimations of the parameters, let's say, of a line that you are doing. And both of those things themselves will be random variables. So you will never know what is your actually expected value, but you can estimate it based on different factors. So if you just want to imagine kind of more intuitive explanation of this, the variance is basically the difference between subsequent runs of the algorithm. If you get similar amount of data from similar kind of underlying reality, and you run your algorithm multiple times, the results you are getting could be very close to each other, and that means low variance, or they could be very far from each other, that means high variance. On the other side, the bias is basically how far the average of your results is from the true result. So again, you can have low bias, meaning generally you are close to the solution, or you can have high bias, which means you are consistently off from the solution. And of course, you can have any combination of those. You always want to have low bias and low variance, because that means that every single time you are doing learning, you are getting very close to the solution. But you might have one of those high, the other one low, or vice versa, or you could have both of those high. And you can see on the pictures what that means. I think intuitively, that's quite easy to understand. The question is, of course, how do you deal with it? How do you make sure that you end up in the top left corner of this picture and not in the bottom right corner? So again, you can do quite a bit of kind of mathematical analysis of how this is done. I will not go into the exact details here, but it's useful to know that you actually can figure out, if you do training several times, you can figure out which of those factors is more important for you in a particular problem. So if we just talk a little bit more concretely about what you can actually do. So let's say we are interested in figuring out good hypothesis representation. We have a very simple problem, deciding whether a particular person will enjoy playing sports or not. So our training data could be like this. We have 6 different attributes, whether sky is sunny or rainy, whether temperature is warm or cold, and so on. We have 4 different training examples. In 3 of the cases, the person enjoyed sports. In 1 case, they didn't. So we have our target concept, yes or no. This is what we want to learn. So based on those examples, we want to generalize to kind of get some kind of hypothesis, which will tell us for new data points what the person will decide. So the first question we need to do is we need to decide how we are going to represent the hypothesis. And we could talk, you could imagine this as a 6-dimensional space. You could try to draw a plot of 6-dimensional space. That's not easy. So you generally need to think about a kind of more maybe symbolical representations. So one way of coming up with a representation will be to say, we are interested in just a simple conjunction on attributes. So we could either say that a particular feature needs to have a specific value, for example, water is warm, or that we don't care about the value of this feature. So we are happy with whatever temperature of the water. It's also useful to have a hypothesis which is always false. So basically to say that there is a hypothesis which no example can ever satisfy. If we have those three cases, we could have a hypothesis like this. So sky is sunny, we don't care about temperature, we don't care about humidity, wind is strong, we don't care about water temperature, and the forecast is the same. Based on those 4 examples in the table, what should be the target for this, or label for this hypothesis? Should this hypothesis correspond to person enjoying sports or person not enjoying sports? Any guesses?
Yes.
Enjoying sports?
Yeah.
Enjoying sports, very good. So one important thing is that when you have hypotheses represented in a particular way, you can also talk about the hierarchy of hypotheses. So you can have different types of hypotheses, and it turns out that some of those will be more general than others. This will not be a complete ordering. There will be some hypotheses which you cannot compare, but you will be able to say about some of the hypotheses that they are more or less general. And the reason why you can do this is because each hypothesis corresponds to a subset of examples. At least in this easy case where it's a binary hypothesis, something is either true or false. So basically every hypothesis corresponds to a set of examples that it classifies as being true. And if you think about this, on sets, you have this partial ordering. You have sets which are subsets of others. So here, for example, you could imagine if x1 and x2 are the examples, sunny, warm, high, strong, cool, same, you can have those 3 hypotheses, h1, h2, h3, described like this. And here you can see that h2 is more general than h1. So basically, every example which is classified as true by h2 will also be classified as true by h1, right? And that's very easy to see. On the other hand, there is no such relation between h1 and h3. Those are not comparable in this sense. And this is important because what you want to be looking at is you want to be looking at relations between those kinds of hypotheses. So you want your training to give you a hypothesis which covers all of your positive examples, so which correctly classifies the examples that you have. But then there will be a number of hypotheses that fulfill this condition, unless you have a lot of examples. And then you want to be able to describe those hypotheses in different ways. And the specific general relation is definitely one interesting case. So one possible way of doing learning would be to just try to search always for the most specific hypothesis which covers all the positive examples. And this is a very simple algorithm for doing that. So you could imagine that we start with a hypothesis which is the most specific in our hypothesis space. And then we just go through each positive training example, and we have 2 possibilities. Either this training example, each attribute is already satisfied by our hypothesis, in which case we don't need to do anything, or this constraint is not satisfied, in which case we will replace this constraint with something more general. Once we are done with that, we have a hypothesis which covers all of our positive examples. And if we just look at one kind of use case for this, so we have those 4 examples that we had before, x1 to x4. We start with the most specific hypothesis. The most specific hypothesis is something that says the person never enjoys sports. That there is nothing more specific than that. And then we go through examples one by one. So we see x1, and basically it turns out that our hypothesis is not good enough because it doesn't cover this example. This example says that under those conditions, a person will enjoy sports. Our hypothesis says the person will not. So we need to update our hypothesis. So we basically go through every attribute and we replace the existing condition with something more general. So in this case, we will basically just replace those empty sets with the values for the attributes. And now we have hypothesis H1, which says that the person will only enjoy sports if it's sunny, warm, normal, strong, warm, and same. This is a very specific hypothesis, but it's consistent with the one example we have identified. So for now, we are happy. We look at the second example, and turns out that our hypothesis still isn't good enough. We need to improve it. And now it becomes maybe slightly more interesting, because now when we go through attributes one by one, it turns out that we don't need to do anything special about the first attribute. It's already covering the new example. We don't have to do anything special about the second attribute. It's also fine. Then we come to the third attribute, and we notice that our hypothesis says that the person will only enjoy sports if, actually don't remember what that was, maybe wind was normal. Probably not, something else, maybe. But I've forgotten what was, humidity was normal. That's complicated. So if humidity was normal. Now we see an example where the person actually enjoys sports if the humidity is high. So we say, well, actually, apparently, humidity is not very important for that person. The person can enjoy sports both in normal and high humidity. So we basically say that, okay, humidity doesn't matter. We replace it with a question mark. And then the other three attributes work just fine. So now we have hypothesis 2, which is more general than hypothesis 1, and it covers examples 1 and 2. So we are kind of happy. Then we see example X3, but that's not interesting because that's negative example. We only care about days on which a person enjoys sports. Then we go to example 4. Turns out that we need to replace the last two attributes with question marks as well. And when we do it, we have hypothesis 4, which is the most specific hypothesis, which covers all of our training examples. And that's one way of doing it. That looks quite interesting. It seems to be a nice hypothesis, which kind of makes sense. There is one challenge with doing something like this, of course, which is basically that if you look carefully about what happened here, there is an inductive leap which is not entirely obvious. So if we have those two examples, and we are trying to say that the most specific hypothesis, which covers both of those, is basically sunny, warm, normal, and then three question marks. This is not entirely obvious, right? Because the question is, why would we believe this? What about those two examples allows us to classify those unseen examples, right? Because if we say that our new hypothesis is sunny, warm, normal, and three question marks, that means that a new example, sunny, warm, normal, strong, warm, same, will be classified as positive example, even though we have never seen an example like this. We don't know what the decision should be. Right? So this is why we are calling this inductive leap. We are kind of making a guess about what will happen on the unseen examples. But that's the core of machine learning. That's what we want to do. We always want to make those kind of generalization steps where we say, based on, let's say, those two examples, we will make certain predictions about examples we haven't seen yet. And the whole point is, are we making those predictions correctly or not? So in this particular case, the question is, how do we know that we should make this particular inductive leap? How do we know that this is the right hypothesis and not something else? Because one possibility would be to have what is called an unbiased learner, where we basically have a hypothesis space which is capable of expressing every possible concept. So the hypothesis space would be the power set of space of examples. Again, we've talked about each hypothesis is a set of examples. So if we can represent every possible subset of X, then we would have a space of hypotheses which could learn potentially anything. One example that we would want to do this would be, let's say instead of our question marks, we also add more operators. So for example, we allow disjunctions, we allow conjunctions, we allow negations. So we could have a hypothesis like this: if it's sunny, warm, and doesn't matter the rest, or if whatever the values of first 5 attributes, but not change. That could be one possible representation of a hypothesis. It makes at least some level of sense. The question is, what would be the most specific and the most general hypothesis if we allow this kind of conjunctions, disjunctions, negations, and so on? The problem is, in this case, we wouldn't actually learn anything, because if we are looking at the most specific hypothesis based on those two examples, the most specific hypothesis would be sunny, warm, normal, strong, cool, change, or sunny, warm, normal, light, warm, same, and nothing else. So we could have a hypothesis which covers those two examples and nothing else. That would be the most specific hypothesis. The most general hypothesis, of course, the opposite of specific, would be hypothesis which says the person will enjoy sports every time. So if we just look at most specific and general hypotheses in a language which can express any subset of examples, we would never learn anything. There would be no generalization. So in our particular case, we were doing generalization because there was no way of covering only those two examples. If we replace one attribute with a question mark, we automatically cover more than those two examples. And that's the general idea that underlies every machine learning algorithm, that whenever you learn something from a subset of examples, you make those inductive jumps or leaps, and you actually make predictions about examples which you haven't seen. So one example of such an algorithm that works would be a decision tree. So this is probably the most popular machine learning method. One of the benefits is that it's very intuitive for people. Like, it really is very similar to how we are doing our decision making. And so the decision tree could look something like this. You have test in a particular node. So you test if the first attribute is bigger than alpha. And if it is bigger than alpha, then you take left branch. If it's not, you take the right branch. Then you will have another test. And based on this, you will again go left or right until you reach a leaf in which there will be some decision. So for example, you might have a tree that tries to distinguish between cats and dogs. Okay, this is very, very familiar for people. That makes sense. And we like this divide and conquer idea. Right? And the core of why this works is basically we split the data into smaller and smaller chunks. After every node in a tree, we look at a single attribute, we make a decision based on the value of this attribute, and then we don't need to consider all the data anymore. We have now gotten a better, smaller subset of data, hopefully one which is not as difficult to analyze as the one that we started with. So in practice, in decision trees, you have single variables in each of the nodes. It doesn't have to be like this. You can do it in a more complex ways, but usually it's not really worth it. Even with single attributes, you can represent any function you want as a decision tree, but it will be potentially a very big decision tree. So in the end, what you will end up with is a model which is a combination of axis parallel rectangles. So every split you get here will correspond to a single thresholding in your space. If you have a lot of those thresholding, you can approximate any kind of function, but the more this function looks like a rectangle in the space, the easier it is to learn the particular tree. So if we look at a simple example, the iris data set, which describes different kinds of flowers, well, 3 different species of flowers. Here is one example of how a decision tree could look like. So based on the 4 parameters that you can have, the petal width, petal length, you can split the data. So for example, if you look at the very top, if the petal width is less than 0.8 centimeters, then you know this is a particular species called Setosa. And if it's bigger than 0.8 centimeters, then you have to keep thinking basically about what species could that be. And if you look at how this looks in space, you could draw something like this, where you have different classes in different areas. Again, I will not go in too much into details. If we look at yet another example of problem, let's say we want to decide if we wait in a particular restaurant or if we go somewhere else. So it's Saturday, or well, it's some kind of dinner time. You want to go to eat something, but the restaurant is, you encounter a restaurant, and the question is, should you eat here or should you keep looking? So here is the true function. So this is the actual decision that we kind of want to replicate. And then the question is, could we learn a tree like this from some number of examples? So if we think of it, here we have 10 different attributes. Most of those are binary, but they don't have to be binary. Then there can be different types of attributes. Let's say here is our training data. We have 12 training examples. In 6 cases, the person decides to wait in this restaurant. In 6 cases, the person decides to go somewhere else. How can we reconstruct the decision tree from this? So one way of doing decision trees would be to just have a tree in which you have 1 leaf per example. So for every example, you would have 1 leaf. You would have branches going up based on all the values of this attribute. So it will be some kind of memory-based learning. And this is not really what we want to do, because it will have very bad generalization. We would only focus on individual examples. What we want to find is we want to find common patterns that kind of aggregate or combine a lot of different examples. So what we really want to do is we want to find a small tree which still captures our decisions. The problem is that learning good decision trees is hard. It's an NP-complete problem to find the smallest decision tree which is consistent with a number with our examples. So in practice, we always do it in a greedy way. So what we will do is we will look at different variables, different attributes, and we will pick the one that seems to be the best, basically, which somehow increases the purity of the data the most. Hopefully, what we can do is we can find an attribute which, if we split based on this attribute, you will have all the yes samples on the left, all the no samples on the right, and the decision will be trivial. In most cases, you cannot do it in a single step, so you will want to find some way of splitting it in such a way that you have as many or as clear decisions later on as possible. So if we cannot have completely pure nodes, we will have some measure of purity. One possibility is to use entropy. So if you look at entropy, this is a measure of the order in a system. So you want to have entropy which is maximal when all the possibilities are equally likely, and then the goal is to decrease the entropy as you go deeper into the nodes of a tree. So entropy will be 0 in a pure node, so node where all the data is either yes or no. And you can calculate entropy based on this simple equation. It's just p times log of p, and you summarize over all the possible values. And this is how it looks like. Again, the entropy is highest if the probability of yes is equal to 0.5, because that means probability of no is also 0.5. And then as you get farther away from this balanced case, the purity decreases. And this comes from the thermodynamics. Here are some examples of how it looks like. You can start with entropy being 0 if all the examples are in the yes class. And then as you get more and more no examples, the entropy increases. It goes to roughly 0.7 when the yes and no are equally likely. And then again, it starts to decrease until it reaches 0 when there are only no examples. So if you think about how you can use entropy to create decision trees, you would start with a full training data set, and you would do recursive algorithm, where at the beginning, you measure the entropy of the data set, and then you can calculate how much the entropy will decrease if you split on individual attributes. Then you commit to a split which leads to largest decrease. You repeat this for every resulting node. At the end, you will create pure nodes, and this way you will, in a greedy fashion, build a tree which looks at least somewhat reasonable. So if we go back to our example and we see how it looks like, we have 6 true and 6 false examples here. So if you look at the entropy, easy to calculate, this is 0.3. And then what we want to do is we want to look at the attributes one by one. So we check is there an alternate restaurant we can see attribute. If we would split based on this attribute, we would end up with 2 nodes. The yes node, which would have 3 positive, 3 negative examples, and with the no node, which would also have 3 positive, 3 negative examples. If we calculate the entropy here, it's also 0.3. So splitting by this actually doesn't help us at all. Next attribute, is there a bar? We could do the same thing, exactly the same entropy, still no decrease, not useful. Then we could look at, is this Saturday, Friday, or not, or is it a working day? Now we see something potentially interesting, because now we have in one of the subnodes, we have 2 positive examples and 3 negative examples, and in the second, we have 4 positive, 3 negative. So now it's not going to be exactly 50-50 flip anymore, and we can see this in the entropy. If we calculate the entropy for this case, it's 0.29, which is smaller than 0.3. So we actually have our first entropy decrease. But we can hopefully do better. If we look at how hungry we are, we get a slightly better split. Entropy is 0.24, bigger decrease. And we can keep doing this for a number of different attributes. I will not go in detail through all of those. You can see it. But basically, what turns out is that the largest entropy decrease we got was when we are splitting by patrons. So if we look at how many people are there in the restaurant, there can be nobody, there can be some, or there can be full. And the reason why this gives us such a good entropy decrease is basically that what we end up with is we end up with 2 nodes which are pure. If there is nobody in a restaurant, you don't want to go there. If there are some people, okay, let's go there. And then if the restaurant is full, then you need to make some more decisions. And so in this particular case, we have 2 pure nodes, and then if the restaurant is full, we end up with 4 negative and 2 positive examples. So this is something that we will need to continue splitting. So we decide at the top of our tree will be patrons, and then we will keep splitting the rest. And again, this goes back to the idea of what is the inductive leap, or what is the generalization we are making here. There is infinitely many possible examples which have no patrons in the restaurant, or which have some patrons in the restaurant. For all of those, based on just those 12 that we have seen, we are now making a decision that whenever the restaurant is empty, we will never go there. Whenever the restaurant has some patrons, we will always stay. So this is the kind of guess or prediction that the decision tree makes in this case. And now we are committing to this. We will never change this decision, right? So this is the generalization that underlies this particular, at least, algorithm for machine learning. We don't know if those decisions are correct or not. But we haven't seen anything in the examples we've been given that would give us other kinds of hints. So we are saying this makes sense. We will make those kinds of assumptions. And then in case when there is full patterns, we will again calculate the entropy for a smaller data set. Now we only have 6 examples that we need to deal with. We can calculate entropy, we can go through all the other attributes, figure out the decrease, find out what's the best one. So this is the tree that we can get out of those 12 examples. This is not exactly the tree that we started with, right? It's not a perfect match. It's a pretty good match at the top, and then it becomes much more, quite a bit different at the bottom. And the reason, of course, is that 12 examples is not really enough to find all the patterns. Right? So if we would have more examples, we would have been able to recover the full tree. In this case, we have not been able to do it perfectly. We have been able to find the top of the tree, but the rest of it, we just didn't have enough data to train. So this is kind of the example of how this works in practice. And then, of course, the question becomes, so how do we know if our tree is good enough or not? How do we know that the hypothesis that we have came up with is actually at least similar to the one that we are really looking for? And there is no real answer. I mean, there's a philosophical problem. How do we know that the sun will rise up tomorrow? We have only seen it, well, some number of millions of times. There is no guarantee that it will continue happening, but it seems quite likely. So basically, one way of figuring it out is to try our hypothesis on a new set of examples, the ones which we haven't used in training. Because the problem is, if we take our decision tree and we try it on the examples that we have trained it on, we know it will fit. We have created it in such a way that it will never make any mistakes on those examples. So that fact doesn't tell us anything about how well it will behave in the future. So the only reasonable way of checking if our method actually works, if our hypothesis is a good one, is to test it on a new examples which we have not used during training. And again, this is based on this principle of uniformity, the IID assumption, that whatever results we get on the test data should indicate the results on the future data if those data comes from the same distribution. We cannot try to believe the results we are getting on training data set that they will generalize to future data because we have adapted our hypothesis to this training data set. So even though it comes from the same distribution, for our hypothesis, it's not the same as future data because we have already seen it. We have created a tree or anything else that is well suited for this particular data. But if we have some leftover data which we haven't used for training, then we can assume that it will still be indicative of the results in the future. And the basic idea is that if we are trying to, or if we believe that we have found the actual causal relations in the data, we assume this causality will be constant. If there is some reason for making the decisions, let's say about the restaurants, we assume this will not change. And again, this is an assumption. There are different techniques that you can do if you don't, if you want to go beyond this kind of assumption, if you assume that things will change in the future, things like concept drift and so on, but this is beyond at least today's lecture. So one way of looking at doing this kind of validation is with validation set. So before you start your training, you split the data into 2 parts. You use one part for training, and then you use the other part for validating your model. And then you can have expectations that the generalization error will be approximately similar to the validation error. And you can also do it using what is called k-fold cross-validation. So basically, instead of splitting this once, you can make several different splits and train on different subsets of data, and then validate on unseen data. This is just a way of getting this slightly more efficient. This is quite simple. And the main problem, or the main reason why we need to be doing something like this, is that if you think about the complexity of learning, it can be done in terms of number of examples from which you are learning. It can be done in terms of how big the decision tree you are making. Any other way of looking at it is basically that, or number of iterations for neural network. As you get more and more complex models, your training error will continue to decrease, again, unless we have very simple data and we reach zero. But assuming we have complicated enough data, we will never reach zero error, so we can continuously decrease the error on the training data. But your error on the test data will actually at some point start to increase. This is a concept called overfitting. So this is obviously not something that we want, because we don't care about increasing or decreasing the training error if our test error grows. So we want to find a place where our test error is the lowest. And one way of doing it is kind of experimentally. You can keep training and keep evaluating or validating your results until you see the test results grow up. But we are also interested in figuring out how can we actually relate those two things? Can we quantify the relation between the complexity and the training error and the test error? So one way of looking at it is in the complexity theory. Let's say that we consider a simple space of hypotheses where we just have m of those. We have from h1 to hm, and we just want to pick the one which fits our data the best. So let's say those could be some randomly chosen linear classifiers. Then the key question is, if we have n training examples and m possible classifiers, what's the maximum difference between training and test errors? Can we actually make certain assumptions about how far apart those two errors can be? And from that, of course, we are interested in saying, so if we swap this a little bit, how many training examples we need, and before we expect the errors to be sufficiently close, whatever sufficiently means here. And it's quite clear that the answer to this will depend on m, depending on how many different classifiers we are choosing. So if you look at the empirical error, so the first line, the epsilon with a hat, so you can measure the error of a hypothesis on the training set. That part is easy, and you can just say there is 1 for every mistake the classifier makes and 0 for every time it makes a correct prediction, or you can measure this loss in any other way you want. And then from this, we can treat this as a random variable, and we can calculate the expected error of this hypothesis on all of the data drawn from the particular distribution. So for any of our finite hypotheses, we can calculate both of those things. And then what we could do is we could pick the one that minimizes the training error. If we have finite number of hypotheses, that's very easy to do. Right? You just calculate it for all, and you pick the minimum value. Now, if we do this, we can rewrite our questions in a more formal way. So now, given n training examples and m possible classifiers, what is the smallest epsilon such that the maximum error we make is smaller than this epsilon? And at the same time, for a particular epsilon, how many training examples do we need so that we get the training error which is smaller than this epsilon? Now, There is no way to answer those questions in a kind of deterministic fashion, because we know that our examples are sampled at random. So we might get very unlucky and end up with very bad examples which don't really, we are not really representative for most of the data. So we need to address those questions in a probabilistic fashion. But if we can just do some simple experiments, that's one way of doing it. Right? We can create a whole bunch of points according to particular distribution. We can create a number of classifiers, and we can see if we do it for different number of classifiers, what we are getting. It basically turns out, as you can see here, that the more classifiers you have, the higher the expected or the maximum error that you will end up with. So let's see if we can understand where this kind of picture comes from. So the basic theory that underlies those kinds of concepts is called probably approximately correct. And I think that's a very funny name, because it basically tells us that what we are doing, everything we do in machine learning, probably is approximately correct. So the whole intuition behind it is that if you have a hypothesis which is consistent with a large set of training examples, it's unlikely to be a really bad hypothesis, right? And then the question becomes, how can we actually formalize this relationship between the hypothesis space size, the generalization error that we can get, and the number of samples that we need to achieve this generalization error? I will not go too deeply into the math behind it, but I will go a little bit through some of the examples. So one way of looking at it is we have our n examples, m hypothesis that we consider, and the epsilon, which is the error that we are interested in. So basically, one way of looking at it is we could require that with high probability, the empirical errors of all classifiers are close to their expected errors. So you can calculate this based on the choice of training set. And basically, depending on how likely it is that your training examples are really not representative for the full distribution. The alternative way of looking at it is you could also bound the probability that the error of a single classifier is bigger than epsilon by just 1 minus this delta. But if you think of it in kind of more intuitive sense again, what we are interested in is we have some kind of instance space X, and we know that we sample examples from this space based on distribution P. And then what we have is we basically have our underlying true function that we are trying to approximate and our hypothesis. And clearly, there will be some number of instances on which those disagree, right? So there will be some area which is common between those where they agree and some area where they don't. So basically, you can measure the error of a hypothesis based on what's the probability that for a randomly chosen example, the hypothesis disagrees with the function that you are trying to learn. So if you look at it very, very simply from probabilistic perspective, let's say we have such a bad hypothesis, right? The hypothesis for which the overall error is bigger than epsilon. Now, what's the probability that this hypothesis will look good when we only consider it through the lenses of training set? So we have our training set with n samples. What's the probability that this hypothesis will be consistent with our training set? The reason why this is so important is basically, if we can see from the training set that the hypothesis is bad, we don't care about it because we will never pick it as our hypothesis. So we are only afraid of situations where we actually pick a bad hypothesis because it looks good based on the training set. So we have n samples. What's the probability that such a hypothesis will agree with all of those samples? If we have our bad hypothesis, probability that it's inconsistent with one sample is by definition epsilon. And that's exactly what the error is. So if we pick random example, the probability that this hypothesis is wrong on this example is epsilon. That means that probability that our hypothesis is consistent with one sample is 1 minus error of h, so 1 minus epsilon. And then the probability that our hypothesis h is consistent with n independently drawn samples is 1 minus epsilon to the power of n. So here there are two important things to consider. One is we are assuming that our training set of n examples is independently drawn from the original distribution. If the samples are not independent, this kind of equation or inequality will not hold anymore. And so this is why it's so important, this independent and identically distributed assumption. But if we have our training set of n examples, the probability that a bad hypothesis is consistent with all of those is very, very low, exponentially low. So that's one of the underlying things about machine learning. So then, if we want to, that was talking about the single hypothesis, right? Now the question is, if we have our hypothesis space, which contains a lot of different hypotheses that we evaluate all of them, what's the probability that within this set of bad hypotheses, there is at least one which is consistent with our training set? So now this is slightly harder, but you can still put certain boundaries on it. So basically you want to say there is a hypothesis is both consistent and it has high error. So this will of course depend on how many bad hypotheses you started with. The more bad hypotheses you allow in your hypothesis space, the more likely it is that you will find one which is consistent with your data. And then again, if we want this to be smaller than a particular constant, what we can say is something like this. So here we basically can look at, we need to have a certain number of examples in order to guarantee that the probability that we pick a bad hypothesis is sufficiently low. So basically what we look at is we have three different factors that are combined here in interesting ways. So basically we can connect the number of training examples, the size of the hypothesis space that we consider, and the probability of making an error. And we basically say that if we have very, very large hypothesis space, if we allow very complicated models with a lot of degrees of freedom, then we will probably not be able to learn very well unless our number of examples is also very high. On the other hand, if we have a very constrained hypothesis space, if we only allow simple models, then we need less examples in order to find good hypothesis, assuming it's consistent. So this is a very important property that basically, if you want to know how much you can be overfitting, the more complicated models you allow and the less examples you have, the more likely you are to be overfitting. So this was still quite, we didn't really go into too much details about, like, so how many do you need? Like, do you need 100? Do you need 1,000? Because that's very difficult to actually measure. So it's not really possible to put concrete numbers on those things. But there are some ways of looking at it. And one way of actually becoming even more concrete in terms of when you can learn successfully and when you cannot is when you start looking at what is called VC dimension. So VC dimension is basically a measure of how much you can learn by a particular type of algorithm from a particular space of functions. So you can talk about this in terms of the complexity or expressive power of different functions. So just to give you some examples, the VC dimension of linear classifier would be 3. The VC dimension of neural network with E edges is O of E. I think I'm running out of battery. I should probably get a charger. Yeah, if you could bring from my room. Thanks. So those are just some examples. And this idea is based on the concept of shattering. So what you can imagine is, you can imagine a number of points in, let's say, two-dimensional space. And the question is, how many linear classifiers, or how many different classifiers from a particular set you need to generate all n to the power of n distinct labelings. So if you look at the example here, if you have 3 points in a two-dimensional space and you have linear classifier, you can shatter those 3 points. So basically, you can assign any possible labeling to those 3 points. And here are all the possible examples. In the top left corner, you have all 3 points are positive and there is nothing that's negative. But for any combination, you can find a line which will give you the kind of decision boundary that you are looking for. But you cannot do the same thing for 4 points, right? If you have 4 points, for example, representing the XOR function, you cannot shatter those with a linear classifier. There is no line that you can create that will separate those things. And you can generalize this to more complicated both classifiers and to higher dimensional spaces. So for example, if you have a set of d-dimensional linear classifiers, you can shatter exactly d+1 points. So then the VC dimension is a set of classifier, is the number of points that this set of classifiers can shatter. And of course, if instead of linear classifiers, you would have more complicated classifier, like a decision tree of a particular size or something like this, it would be able to shatter larger set of points. And the reason why this is so important is that basically the only way you can do learning is after you can no longer shatter the training points. So if you have less training examples than the VC dimension of the hypothesis space that you are considering, you cannot do any kind of learning. So basically, you always need more than DVC training examples. And if you think about why, that's quite an easy way of explaining this is, if you consider that you have n training examples, which is less than VC dimension, the question is then, does this training set constrain our prediction of the next example? So example number xn+1. If we know that we can shatter n+1 points, so we can find any labeling for those points, that basically means that we have 2 different hypotheses, H1 and H2, that both belong to our data set, to our hypothesis space that we are considering. Both are consistent with our training set of endpoints, but the two hypotheses will give us different labels for point number x n plus 1. By definition of VC dimension, we can always find it, because for any set of n plus 1 points, we can find any possible labeling. So we will be able to find the labeling which agrees on the first n points but disagrees on the second. So basically, that means that we don't know what to predict for our next example. We have two hypotheses. They are both equally good on the data that we have seen, but they differ on the new example that we are trying to predict. So we have no way of figuring out which of those would be better. So that's why it's so important to say that we need to have sufficiently many examples, because if our number of examples is bigger than VC dimension of the set of classifiers, then we cannot do it. Then we will know that it's not possible to find two such hypotheses. So we can pick a hypothesis which is well either consistent or at least more consistent with the training set, and it will give us a concrete labeling for the new data set. And this goes also, in a sense, to the concept of combining classifiers. So we know that there is no single best classifier based on the no free lunch theorem. We know that every classification algorithm needs to make certain guesses about the predictions for future data, because it needs to make those inductive leaps. And we also know that for different problems, different classifiers will be better, because the inherent bias of those classifiers will better fit our particular problem. The challenge is, of course, how do we know which classifier is best for the particular problem that we are trying to solve? So one possibility is, of course, to try different classifiers and see which one works better. That's one way of doing it. But another way of doing it is also, if we already know that we have many different classifiers, can we actually combine them somehow to get results which are better than any single one of those? Because we could pick the best, but maybe if we find good way of combining them, we can get better than the best of those. And it turns out that you generally can do it. So if you have many classifiers and you try to combine them under certain assumptions, you can get better results than the best of the classifiers that you have tried. So there are two key requirements for something like this to work. They have to be making uncorrelated errors, and they have to perform better than random guess. So basically, if you have a classifier which is just as good as random guess or worse, you cannot really make anything out of it. You have to be getting at least some insight from the classifier. And also, if you want to combine classifiers, they have to be different. It doesn't make sense to try to combine classifiers which always make the same kinds of errors. So if you think about this, it's not necessarily easy to make those, especially the uncorrelated assumption is quite strong. But if you think about, you have Pi, which is bigger than 0.5, is the probability that classifier, actually it should be smaller than 0.5, probability that classifier I makes a mistake. That wasn't smart. Share screen. Let me see if I can get back. Can you still see my screen?
Yes.
Okay, good. So if you have a classifier I, which makes mistake with probability smaller than 0.5, then, and you have k such classifiers, they all make such mistakes and they are uncorrelated. That means they are making those mistakes independently. So the probability that all k will make a mistake is pi to the power of k, which is much smaller than pi. And then basically you don't even need all of them to make mistakes. If at least half of them, or if less than half of them makes a mistake, then you can just do simple majority voting and end up with the correct decision. So basically, if you can create infinitely many such classifiers, then just by majority voting, you can reach arbitrarily high accuracy. You can go all the way to 100% accuracy. The problem, of course, is that we can never get infinitely many independent classifiers. That doesn't work. But maybe we can get some number of them. Even if we don't go to infinity, we cannot reach 100% accuracy, but we can still do something interesting. And if you think about why such combinations of classifiers, also called ensembles, would work, there are basically three main reasons for why they can outperform individual classifiers. So one is what is called statistical reason, which is basically that this goes back to the variance that I was describing. Each individual classifier will make a certain error, but if those errors are uncorrelated, the average of those will be closer to the true function that you are looking for. The second reason is computational reason. If you imagine that the classifiers could potentially be able to find the optimal solution, but the problem is just computationally too difficult. Right? If we would say that the optimal decision tree would be correct, would actually capture our target f function correctly, but we know that this is an NP-complete problem. If you have 1,000 examples, you cannot find the optimal tree for this. But if you imagine that you combine several different trees, potentially they are moving in the direction of function f from different directions, so the average of those would be closer than any individual one. And the third reason is the representational reason. So if the target function that we are trying to capture is actually outside of our hypothesis space, so let's say that we only allow trees with at most 1,000 nodes, but the actual function f would require 2,000 nodes. We can never find it. But if we find a number of trees, their combination that might be closer to the true function, than would be possible with a single hypothesis from our space. So those are three possible explanations for why ensembles can work. The most important reason, of course, is that they actually do work in practice. So that's why it's so important to talk about them. So if we assume that we have a number of classifiers and we want to find ways of combining them, the question is, of course, how should we combine those decisions? And the most popular is by voting. So basically, what we are looking at is we are looking at how many classifiers suggest a particular decision, and then we pick the decision which has the most support, which most classifiers vote for. And either this can be just counting the classifiers, or it can be some kind of weighted voting, for example, based on the performance of different classifiers. So the classifiers that are performing better will have higher weights. You can also do this in non-voting manner. So for example, you can use some kind of meta classifier. One possible setting is you have a number of classifiers that each make decisions, and then you have a classifier kind of on top of them, which tries to figure out, based on different combinations of decisions, from the base classifiers, what should be the correct decision. And then the other important distinction is which members are actually used to classify new example. So again, the most common solution is the group-based approach, where basically whenever you get a new example that you want to classify, all the classifiers will be consulted, and you will do, for example, some kind of voting. But there are also methods which try to train specialized classifiers for particular types of examples. It could be different areas in decision space or something like this. So basically, you would try to have member classifiers which are experts in different types of examples. I will not go too much into details here, because I want to focus on different ways of making diversification. So as I said, the core idea behind ensembles is that you need to be able to create a number of classifiers that make independent decisions. And there are several different ways in which you can try to make those diversification. So the most common one is with training sets, where you basically will use different data for training your classifiers. Another popular approach is with different learning algorithms. So you would combine, for example, neural networks and decision trees and support vector machines under the assumption that those will be different. You can do different subsets of attributes. You can choose different parameters for your algorithms. You can do different architectures, that's mostly for neural networks. Or you can just do different kinds of initializations. So most of those algorithms are some kind of randomized algorithms. So if you initialize them differently, they might end up in different places. So another important thing about ensembles is that they actually solve they address the bias and variance errors in different ways. So if you look at the idea of heterogeneous classifiers, so those would be using different algorithms for your base classifiers. And that's actually not that popular, because it's difficult to measure and control how diverse the results really are. You don't have that many different algorithms. If you want to make a large ensemble, this actually doesn't work so well. So homogeneous classifiers are much more popular, where you are basically using the same classification algorithm, but with different kind of input parameters in order to create your ensemble. And here, there are three different ways of doing it. One is called bugging, which basically aims to reduce the variance error component. And the idea here is that bugging will create many different models based on different subsets of the data. So you will try to reduce the error that comes from a particular selection of the training data by retraining multiple times on different subsets of this data. Another approach is called boosting, which mostly aims to reduce the bias error component. And boosting will try to create in a sense, sequence of classifiers in such a way that every next classifier improves upon the previous one. So you will look at what kind of errors did a classifier make, and then you will try to make a classifier, a new version of a classifier, which fixes some of the mistakes that the previous one did. So I will talk more about those two as kind of examples. There is a third one, which is called stacking, which basically also reduces error component, and this is about using this combiner classifier, which with the goal of kind of cleverly merging the outputs. But this is much less studied because it's difficult to understand, and it's actually not working significantly better. Again, mainly because it's not so easy to combine a large number of classifiers. So one way of looking at this bugging example is if we start with a concept of decision stamps. So decision stamps would be one way of achieving this goal of many diverse classifiers. So we want to see about how can we make independent errors with decision trees. We want predictions which are independent. One way of doing it is to make very, very simple trees. So for example, like in here, we could do thresholding just on a single attribute. The simplest possible tree we can have is just one level deep. We only have one condition in the root of the tree, and we make decisions based on that. This kind of classifier will not be very accurate, but what we can do is we can create very many of those very quickly, and they are good components because they have low variance, so they will not really overfit, but you can combine a number of those quite easily. So one way of looking at it is random forest, and random forest doesn't really use decision stamps. You can make bigger trees, but the idea behind random forest is that you will draw a sample subset of data. So you have your training set of n data points. You will draw n data points, but with replacement. So some of your data will actually repeat in the training data. And then, based on this sample, you will grow a tree, but at each split, you will only consider a subset of features. When we are building the tree earlier, we went through all the attributes and we picked the one that was the best. Now here, because you want to create a number of such trees and you want them to be independent, you don't want to go through all the attributes all the time because the trees will end up to be too similar. So first what you do is you select a subset of features, let's say M features, randomly, and you only find the best split among those M features, ignoring everything else. So you can keep doing those two things until you create the desired number of trees. And here you actually have two different sources of diversity, because the trees will be different because they come from different data points. There is a different data set that is used to create each of those, and they come from different attributes. So also for every tree, or actually every split in a tree, you have evaluated different subset of attributes. Both of those things are random. So you can actually create a forest of many trees, I mean hundreds of thousands of trees, which will still be quite diverse. And then what you can do is you can just make simple majority voting. So every new example that you want to classify, you will run it through all the trees. Each of those will give you some kind of a decision, and then you do majority voting to find the final outcome. And in addition to the fact that those kinds of approaches actually work quite well, they have one more important benefit, because what you can quite easily notice that for every single tree that you create, you have only used part of the data. And we know which part of the data that particular model has seen, what it was trained on, which means that we also know what data it has never seen before. So if we want to do estimation of accuracy, we have talked before that you can estimate accuracy of a classifier based on the predictions on the data which was not used to train it. And we said that normally we would do it with something like cross-validation. So you would build your model on subset of data, and then you test it on data it has not seen. But that has a problem of you are actually wasting some of your data because you are not using it for training. So here, in case of bugging like random forest, you can actually look at the data. So you pick data sample, and you know that some percentage of trees was not trained on this data sample. So you can use those trees to make predictions, and you can actually get a good unbiased estimation of the generalization error using this, what is called out-of-bag error or out-of-bag data. So first of all, that gives you more data to actually build your model. Second of all, it's also quite a bit faster than doing something like code validation. So that's one important benefit of this. But also, you can estimate feature importance using very similar techniques. So you can basically make predictions on out-of-bag data where you destroy one of the features. And by comparing the performance on the original data and the data with a feature destroyed, you can measure how important this particular feature is for the classification, for decision making. So there are some very useful things that you can get by using bagging ensembles. But there's also the other way of doing ensembles, with the boosting approach, and here I will talk about the AdaBoost algorithm. So this algorithm is based on reweighting the training examples. So you start by assigning weights to examples in a uniform way. So every example is equally important. And then at every iteration of the algorithm, you want to find a classifier for which the weighted classification error is at least 0.5. So again, this goes back to this idea of we need to have classifiers which are better than random guesses. But now we are actually measuring the performance of this classifier based on weighted examples. So we basically say that some examples become more important than others. And the core of this idea is, of course, to look at why some examples should be more important. So we start, as I said, with all the features being, or all the examples being uniform. So we start by saying all examples are equally important. But then we create a new classifier. We assign votes to okay, let's skip that for now. So we create a new classifier and we measure how good this classifier is on the different examples. And what we basically want to say is that the examples which this classifier has missed, the examples which it has made mistakes on, those are problematic examples. Those are examples which need to become more important in the future because we want the next generation classifier to focus on them some more. So we will basically increase the importance of the examples for which we have made mistake and decrease importance of the examples which we have classified correctly. So we update the weights and then we do this again. So we come up with a new classifier. Now the classifier which pays more attention to the examples that we have missed before. So we find such classifier. Now we have two classifiers that we are working with. So we want to combine the results from those two classifiers. So we will assign votes based on the error that each classifier makes. And we end up with right now very small, but we end up with an ensemble that makes a decision for all the examples. And again, now we have new weights for the examples based on how what kind of errors the ensemble has made. If there are some examples which are still problematic, which we still haven't been able to classify correctly, their weights will grow. And we keep doing it. So we basically end up with a sequence of classifiers in such a way that every new classifier is more and more likely to correctly classify the examples that the previous one got wrong. So if we look at how this will look like, we will basically try a number of different classifiers. And because we are reweighting the examples, so here you can see they are becoming bigger, the examples for which we are making more mistakes, we will focus on them more. So at some point, we will stop making mistakes here. And if you look at how this performs, you can actually notice that if you measure exponential loss over all the training examples for all the classifiers in the ensemble, this goes down. And if you look at the classification error on the training data set, it will also go down. And the interesting thing is, you will actually notice that the error of each new classifier that you are adding to the ensemble, that error grows. So every new classifier that you are adding is worse than the previous ones across all of the data set. But because you always combine it with the previous ones, the only important thing is that this new classifier fixes some of the previous problems. It doesn't matter how much mistakes it makes on the examples that have been solved previously, in a sense. I'm oversimplifying this a little bit. But the basic idea is that you can see that both the training and test errors of the combined classifier, when you weight all of those different iterations, this will actually go down. And quite an interesting thing is, you can also notice that this error, that the testing error will keep going down even after the training error is already 0. So even after you are able to correctly classify all training examples, you can still keep learning, and you can actually still get better results on a test data set. So this is pretty much what I wanted to talk about today, the introduction of basic kind of concepts of machine learning, why it works and when it works, the basic algorithms for decision trees, and some discussion about ensemble classifiers. So basically, if you think about kind of the takeaway lessons concerning the machine learning, like rules of thumb of what you want to do in order to get good results, the most important thing is to focus on the hypothesis with low complexity. So whenever you are trying to solve a problem, you always want to at least start with the simple hypothesis. And if that one works well enough, then great. If it doesn't, then it might be worthwhile to come up with more and more complex ones. But you really don't want to start from the complex hypothesis, because it's very likely to overfit. And the way to get to low complexity hypothesis is to basically constrain the hypothesis space with some prior knowledge. So if we know something about the domain, or if we have some reasonable beliefs about how the hypothesis should look like, all of those things are very important for building good models. And this is why it's so important for machine learning data mining experts to work closely with domain experts, because it's very difficult to come up with a kind of general model that will work very well in all the domains. You really want to understand the problem so that you can come up with good hypotheses for this particular problem. And of course, it's very important to use many observations, and the challenge is, in many cases, it's difficult to get a lot of training examples, especially the labeled ones. So it might be useful to not only focus on supervised learning to explore other options, but again, this is not for today. And also the very important thing is to always validate the results you are getting. So it's not enough to actually to just kind of learn the model and say, okay, now I have done the decision tree, I have the decision tree, I've trained it on my data, and it's good. You have to validate how good it actually is using something like cross-validation or out-of-bag error or any other technique for that. So that's it from my side. Any questions?
You mentioned several methods to minimize the errors, both the bias and the variance. And are some of those methods used more commonly than the others in practice?
It's hard to say. It's just like with machine learning algorithms.
Okay.
Some are more popular than others. Some are more popular in some domains. Sometimes for good reasons, sometimes not so much for good reasons. Again, there is no clear winner. There is no method that we can say works best all the time. It all depends on what type of problem you are working with. And the challenge is, of course, that it's difficult to know what kind of problem you are working with, because it's not related to the domain or the industry. You cannot say that in, I don't know, marketing, one method is better, and in predictive maintenance, another method is better. That's not it. It's all about the kind of structures in the data. And usually we don't know the structures in the data before we are done with the analysis. So there are some things that you could look into. For example, there are some things that you can measure. Like if you know that you have very much noise or very little noise, or if you know that you have very highly dimensional data, those are some indicators for where you could say that maybe one method will be better than the other. But those would be just kind of first guesses. We really don't understand those methods well enough to be able to say for which type of problem which method we should use. A lot of this is still empirical.
So this is true also for an experienced person in the field. I mean, if you have both knowledge of the application and knowledge in machine learning, it's still a complicated question to ask.
Yes. Yeah, but that's the important thing. You need to have knowledge in both fields, or at least that doesn't have to be the same person, but you need to at least have a team which has both of those competences. If you don't, then the only thing you can do is you can try a number of techniques and hope that one of the ones you have tried will work. But there is pretty much infinitely many of those. So if you try blindly, you are not very likely to get good results.
No.
How would you go forth to try to find a good method then? Even if you have domain knowledge, do you have to know something about the structure of the data or the type of the data, or is there some guidelines or something?
There are not really that much guidelines. That's the point. But the domain knowledge is important so that you can figure out what can be useful and what cannot. And so, for example, if you think about a decision tree, if you have domain knowledge, you can start thinking of, does it even make sense to build a decision tree? Can I get to good results by doing conditions on attributes one after another? Right? Sometimes you can, sometimes you cannot. Sometimes you need to look at combinations of attributes. So for example, decision trees are not good when you need to compare attributes. Like if the actual condition that you are looking for is x1 is bigger than 3 times x2, then decision tree is not the good method. And again, you will never know the perfect solution, because if you knew, you wouldn't be doing machine learning. But if you have domain knowledge, you can get some idea about what types of patterns you are interested in. But there are no general methods.
Yeah, okay.
I mean, what you can do is things like, for example, random forest generally works pretty well. Right? So what you can do is you just get your data, put it into random forest, you will get some kind of result. That's a starting point. And if that result is good enough, then great. if it isn't, then it becomes tricky. What exactly do you need to do to get better results?
What about the signals that vary in time?
So
here we've been talking about static things, so the weather is this or that. What about something that is varying in time?
So there are different approaches. So there are techniques for learning directly from time series data, but they are generally, I would say, not very good. The most common approach to time series data is to basically create features based on time series that will describe
static
this time series.
Features.
Yes.
Okay.
So we will basically say that in this time series there was a particular periodicity and this medium maximum value, and those features can be they can be simple statistical features like different moments and so on. They can be different types of patterns that you are looking for. So if you know that you are looking for a particular pattern, you can measure how many times it occurred, what was the variation in those occurrences, things like that. So basically you can create static features of any kind you want, but then it becomes even more important to really understand the domain, what kind of things are important.
Will they be independent?
Go on, William, please.
Thank you. I was just thinking about the time series features. Will they be independent of each other's? Like given the condition we were talking about earlier with the IID?
So it depends how you look at it, and also depends what kind of time series you are talking about. So you can talk about time series that comes from different so let's say you have different machines, each of those produces a time series, right? Then the time you can extract features from each of those time series, and they will be just as independent as any other data coming from those machines. If you would look at it in terms of you have data from one machine over a long period of time, and you want to compare maybe month 1, month 2, month 3, then it becomes trickier because then the dependency is much higher, and then it might not necessarily work. But again, it's hard to say, and because it starts to depend on how this machine really operates. If you want to, or if you are interested in detecting like drift because of the wear, then you cannot really treat those as independent. If you assume that the drift because of wear or because of external conditions is negligible, then you can say, okay, I will treat those things as independent. And then it becomes a question of, is it really negligible or were you just wishful thinking?
These error minimizing mechanisms you have presented today, they are just examples, and there are plenty of them, others, I guess, or and
yes. Those are some of the more popular.
It's evolving all the time. Sorry.
Yes, this is continuously evolving. People are coming up with new methods all the time. This is basically where most of the machine learning research is on different methods like this. I guess ensembles, for example, they were very popular maybe 10 years ago. I think now most people are moving to deep learning, so which is kind of slightly different thing. So ensembles are not so popular anymore. I guess at least until maybe in 5 years or so, we can actually start building ensembles of deep learning models. But then we need a lot more GPUs to do that. So we are at least a couple of years away from it.
But is the development mainly driven by academia and mathematicians from theoretical analysis, or is it mainly based on trial and error experiments from anyone?
I guess new methods mostly come from academia because it's difficult in industry to come up with really new methods, right? You would rather try existing ones. It takes a lot of time to develop a new method.
Yeah.
But if you look at something like, for example, random forest, that really doesn't come from mathematicians because it's all random. So that has very much practical roots, because there has been a lot of work on trying to build more clever ensembles, but it turned out that in practice, doing things at random often beats whatever clever thing you are trying to come up with.
I can also add one thing that, I mean, a lot of commercial success for AI comes from supervised machine learning. And supervised machine learning is something which, I mean, scientists have developed for quite a lot of time. And I mean, the kind of applications that you see now from Google and many other speech recognition and biometrics and so on, a lot of that is different variants of supervised machine learning. Supervised machine learning has been, you know, quite developed since like the 80s kind of, and the 80s and 90s and beginning of 2000 and so on. So there's a lot of algorithms and methods that came up then, you know, that has been developed by the academic community for, you know, decades before they sort of become commercialized and went into products the way they are doing right now.
Yeah.
Any more questions or?
Okay, so, maybe not. Great.
So I sent you an interactive tool. So I guess all of you know the link now to the interactive tool, so you can sign up. I don't know, have you tried to do that?
I signed up, yeah.
Did it work? Because Malu tried, and for Malu it didn't work. So have you managed to get inside?
I got in, yeah. I clicked around a little bit and found a questionnaire and stuff like that.
Okay, good. So it's just you, Haran.
For Henrik, it works also.
All right. I don't know exactly how pedagogical it is, but we will continuously try to make it more easy to navigate and so on. We will add content continuously. So the idea is now that you will do some initial exercises for next week, and then hopefully you will be able to get some kind of feedback on that if you manage to do the exercises within 1 week. Because the idea is that sometime middle next week, then hopefully you have answered some of those exercises, so you can get some feedback from one of the course people here, one of the teachers.
Okay, should we do the one called tree-based method quizzes and tree-based method programming?
Yes.
Yes.
Perfect.
Okay.
What about the visualization ones?
You can probably wait with the visualization ones if you can see them. So I'm going to talk to the developer there to I mean, ideally they should be easily connected to the lecture, so you can see when you've had a certain lecture, then these are the ones that you should be doing, and so on. Because
that would help.
The exercise.
For now, it's the two ones on the top we should focus on till next week.
Yes.
Sorry, I interrupted you, Stefan.
No problem.
No, we are kind of still figuring out how to best present, because we have both kind of current content. We don't want to remove everything else, but we probably need to make it more clear about what are the expectations at different times. So we will work on that. Okay. Right. Great. Thank you very much for today.
Thank you. It was very interesting today. Thank you.
Thank you.
Yeah, thank you, guys.
So, bye-bye.
Bye-bye.
Bye.